Hello everyone, welcome to this presentation on understanding Flyn's taxonomy, a gateway to parallel computing architecture. I am Jay and I am excited to walk you through an essential concept in the world of computing, especially as we dive deeper into technologies that demand speed, efficiency, and multitasking. Let's begin with a quick question. Have you ever wondered how your smartphone can play music, download a file, and run a game all at the same time without slowing down? Or how large scientific simulations or AI models are processed so quickly. That's where parallel computing comes in. Unlike traditional computing, which processes tasks one after another, parallel computing breaks a big task into smaller parts and work on them simultaneously. So that's where introduction to parallel computing starts in. Yeah, moving on. This is this not only saves time but is also necessary for today's complex applications, be it real-time gaming, video rendering, AI, or weather prediction models. Now, to understand how computers do this, we turn this into a classic concept introduced by Michael J. Flynn in 1966 called Flynn's taxonomy. Think of it as a framework or a way to categorize how computers process instructions and data. It classifies computer systems into four types based on whether they handle a single or multiple instructions on a single or multiple data streams. So, here are the slides that we talked about. So, proceeding on, visual representation. A diagram illustrating multiple processes handling different tasks simultaneously provides clarity on how parallel computing operates. This visualization helps convey the concepts of parallelism, showcasing how tasks are distributed across processors for improved performance. Let's go through each one with the simple examples and visuals. First, SISD, single instruction, single data. This is most basic model. Imagine one cook in a kitchen following one recipe to make one dish. That's SISD. One instruction working on one piece of data at a time. Your old desktop or a simple microcontroller in your washing machine works like this. It's efficient for small, straightforward tasks but not suitable for high speed or complex operations. Moving on, next, SIMD, single instruction, multiple data. Now what? That same cook making 10 sandwiches using the same recipe on 10 different pieces of bread. That's SIMD. Here's a single instruction is applied across multiple data points at once. This is how graphics processing using GPUs works. They handle thousands of pixels in parallel to render video frames. This model shines in image processing, deep learning, and scientific simulations where the same operation must be repeated over large datasets. Third, we have MISD, multiple instruction, single data. This is the rarest type. It's like multiple cooks using different recipes on a same ingredient. Sounds a bit chaotic, right? That's why you don't see it often in real world applications. But it's also useless. But sorry, it isn't useless. This model is sometimes used in fault tolerant systems like those in spacecraft, where multiple checks are performed on the same data to ensure readability. Finally, we have reached the MIMD, multiple instruction, multiple data. This is the most powerful and flexible model. Imagine several cooks in a kitchen, each using a different recipe to make different dishes at the same time. That's how modern multi-core CPUs, servers, and cloud systems operate. Each processor can perform a different task on different data independently. MIMD is the what Power AI platform, cloud services like AWS, and other multi-services use. To make it even easier to compare, I have prepared a table that shows all four models side by side, highlighting the instructions, flow, data handling, use cases, and real-world examples. Let's now go into the real-world applications and conclusions. Real-world examples, yeah, highlighting the instructions, flow, data handling, use cases, and real-world examples. Let's take a moment now and have a fun quiz. Question: which model does this GPU uses? If you said SIMD, you're absolutely right. GPUs applies the same operations to multiple pixels or data eliminations simultaneously, making SIMD ideal for parallel tasks like rendering graphics or processing neural network layers. Key takeaways. Flame's taxonomy effectively categorizes computer architectures into SISD, SIMD, MISD, and MIMD. Each model uniquely addresses specific computational needs, enhancing performance and efficiency while advancing technologies innovations inherent with modern computing architectures. Further reading and references. For deep insights, read to Computer Architecture, a quantitative approach by Henningsen and Patterson and Michael J. Phelan, original 1966 paper. Yeah, you can have this reference afterwards. Visual summary. Each architecture with Flynn's taxonomy plays a pivotal role access common and advanced computational tasks. Visual aids can further enhance comprehension, illustrating the appropriate applications of SISD, SIMD, MISD, and MIMD in real-world scenarios. So that is for today. Thank you so much for watching. I hope this gave you a clear and visual understanding of how different computational systems handle tasks. If you had liked to learn more, check on the references listed at the end of the videos, including some great books and websites on computer architecture and parallel programming. Thank you.